In this video, we will begin discussing series. To form a series, we take an infinite sequence. So a sub n, as n goes from 1 to infinity, this infinite list of numbers with a definitive order, and then we add up all of the terms in the sequence. Notationally, we express this in sigma notation. We say the sum from n equals 1 to infinity of a sub n. And we call this a series. And typically the question we want to ask is, as we add up this infinite list of numbers, what does it add up to? That language we'll use is, does the series converge to a specific number or does it diverge? But just to get started, does it make sense to add up infinitely many positive numbers? That is, could we ever possibly get back something finite? And the answer is yes, and let me give you a very intuitive example. If I start off with a square that has side length 1, the area of this square is going to obviously be 1. But what we can do is take this square and now start breaking it into parts. So if we cut the square in half, we can think of the left half of the area as being 1/2. And then we're going to add on the remaining portion. But for this remaining 1/2, we're going to break it up into 1/2. So we would have 1/4 as that area. And notice at each step we have this remaining 1/2 that we can continue breaking up. So if we break it up again, 1/2 of a 1/4 would be 1/8. And continuing on one more step, if we break up this remaining portion, that area is going to be 1/16. And we can keep doing this, 1/16 plus 1/32 plus dot, dot, dot. And what we're going to have is an infinite list of numbers that we're adding up. They're all positive numbers, and what they add up to is 1. If we were to write this in sigma notation, the observation that we would like to make is that this is 1/2 plus 1/2 squared plus 1/2 cubed, and so on. So we could express this more compactly as the sum from n equals 1 to infinity of 1/2 raised to the nth power. So it is very reasonable that we can add up infinitely many positive numbers and get back something finite. Specifically in this case, we get back to number 1. Now this series that we saw in our motivating example is a special type of series that provides us with a very nice starting point. A geometric series is a series of the form given here, where you're summing from n equals 1 to infinity of a times r to the n minus 1. And more visually, if we write out these terms, we think of a as being the first term in the geometric series, and then r we refer to as being the common ratio, because if you pick any two subsequent terms, you get from one term to the next by multiplying by r, so the common ratio. And for a geometric series, the a and the r are numbers. The series converges precisely when the absolute value of r is less than 1, and in this case its sum is a over 1 minus r. And recall, when we say the absolute value of r is less than 1, this is equivalent to saying that minus 1 is less than r is less than 1. If the absolute value of r is bigger than or equal to 1, the geometric series is divergent. So if we go back to our previous example, we had this sum from n equals 1 to infinity of 1/2 to the nth power. And I want to think about this in two ways. The first way, I want to match up precisely to what we see above. So we're starting at 1. We need our power to be n minus 1. So an equivalent way to write this would be to pull out one of those 1/2s and write this as 1/2 times 1/2 to the n minus 1. And putting it in this form, we see the immediate comparison. This is a geometric series with a being 1/2 and r being 1/2. Because the absolute value of r is less than 1, this converges to 1/2 over 1 minus 1/2. And and 1/2 divided by 1/2 is simply 1. As it should be from our previous example. Another way to think about this opposed to the more algebraic manipulation is to just write out the series. So this series is 1/2 plus 1/2 squared plus 1/2 cubed, and so on. Now by inspection, we see that A is the first term, and then that value of R is the kind of common ratio. If you're at one term, what do you multiply by to get to the next term? So two different ways to see the values of A and R. So let's now investigate a few examples, and the typical question is going to be, given a series, determine whether it converges or diverges. In this case specifically, since we're going to be dealing with geometric series, if it converges, find its sum. So our first example, the sum from k equals 1 to infinity, 3 over 8 to the k. So just writing this out, we plug in k equals 1, we would have 3 over 8, plus we plug in k equals 2, so 3 over 8 squared, then 3 over 8 cubed, and so on. So purely based upon inspection here, we see that the first term, the A value, it's geometric, is 3/8. And the common ratio, if I'm starting at one term and I'm going to the next, what I'm multiplying by is 1/8. So A is 3/8, the ratio R is 1/8. So because that R value has absolute value less than 1, this tells us that it is a convergent geometric series, and the sum is A, 3/8, divided by R, 1 minus 1/8. So 1 minus 1/8 is 7/8, and 3/8 divided by 7/8, doing just some quick algebra here, is 3/7, which we would refer to as being the sum of the series. Okay, so another very similar example. This time, however, instead of writing out the sequence, what we're going to do is just manipulate it algebraically so we can compare to the formula to determine A and R. And what I'm going to do is just manipulate algebraically the 3 that we have. So this is a sum from n equals 1 to infinity. And I'm going to leave the 2, and I'm going to note that 3 to the 1 minus n. If I instead write this as 1/3, what we have to do is take the opposite of 1 minus n, which is n minus 1. At this point, it's exactly of the form that we would like to see for a geometric sum. N equals 1 to infinity of AR to the n minus 1. So based upon inspection here, our A value is 2. And note the A value does not affect whether the series converges or diverges. The R value determines that completely. Here R equals 1/3, which has absolute value less than 1, so it converges. What the geometric series converges to is A divided by 1 minus R. So 1 minus 1/3 is 2/3, and 2 divided by 2/3 is the number 3. So note, once you recognize you have a geometric series, so something where you're summing up AR to the n, where R is a number, so numbers raised to powers, there's two different ways to efficiently determine the values of A and R. Either manipulate algebraically or write the series out and identify A as the first term and R as the common ratio. Okay, one more example dealing with geometric series. So we want to take the decimal, 0.51, 51, 51, really 0.51 repeating, and we would like to write it as a ratio of two integers. And when we say write it as a ratio of two integers, what we really mean is, can we write it as one number divided by another number? So the observation I want to make is that we can break this up into parts for each of the 51 that repeats. So the first 51 you see would be 51 over 100. The next 51 that you see requires you to take the number 51 and move the decimal place 4 to the left. And then for the next one, we would have to multiply by another note, 1 over 100. So it would be a 1 with now 6 zeros underneath it, and so on. And what we should recognize here is that this is geometric. We have a first term, which is an a value, and if you're at one term and you think about how you get to the next term, you're moving 2 decimal places over. So what you are multiplying by would be 1 over 100. 1 over 100 has absolute value certainly less than 1, so it converges. And the sum of this geometric series would be a, 51 over 100, divided by 1 minus 1 over 100. So 51 over 100 divided by 1 minus 1 over 100 is 99 over 100. So we have 51 99ths, which is equivalent, if we just divide by 3 here, 17 over 33. So starting off with any repeating decimal, you can go through a similar process to recognize it as being some associated geometric series, write its sum, and determine how you can express it as a rational number.